Hi, my name is Katerina, and today I will be presenting to you our work on improving dictionary-based named entity recognition with deep learning. So let's start with the basics. What is dictionary-based named entity recognition? Probably most of you who are following this cozy know what this is, but I will just be very brief in explaining this. So named entity recognition is just recognizing stuff with names. So for example, in the biomedical domain, we want to recognize things like P53 or Alzheimer's disease as genes and diseases, respectively, when we see them in the text. On the other hand, dictionary-based methods, as their name suggests, means that they need a dictionary to detect these entities. And what a dictionary can give us is that, for example, P53 is a gene and Alzheimer's disease is a disease. In order to do this, we use the Jensen Lab Tagger. And this is a tagging engine developed in our lab, which is robust, fast, and as the task requires, it's a dictionary-based tagging engine. And combining the tagger with biomedical dictionaries allows us to extract associations amongst genes, proteins, small molecule compounds, and generally several biomedical entities. And then the text mining results that are obtained from getting these associations are normalized to identifier from suitable databases and ontologies, and then are used in several biological databases that are freely available as a suite of web resources from our lab. And one of the most prolific ones is StringTB. So what makes a good named entity recognition system? There are three things. It has to be fast, it has to have good recall, and good precision. When it comes to speed, the tagger has nothing to fear since it can process thousands of PubMed abstracts per second. And the more threads we have, the faster it works. For recall, we need a comprehensive dictionary in order to be able to detect most of the names that are available in text. And in order to do that, we try to find a lot of sources, or like sources that have a very good and high coverage, or ontologies that do that, in order to generate our dictionaries. And finally, for precision, since we used all of these sources and they can have a lot of names that are not very good, we need some block lists. And block lists are lists of bad names to text mine. These names sometimes are wrong, but they are not necessarily wrong. They can be bad ideas. Like the gene name bad might be a bad idea to text mine. So up to now, what we did for dictionary-based text mining is that we maintained some manually curated block lists, and we have some regular expressions to catch things that are very common in text and we definitely don't want to text mine, like common words like and was. But when it comes to manually curated block lists, in order to generate those, we need to inspect the most frequent names in a large text corpus to identify those that should be disregarded. And as you can imagine, this scales poorly. And for that reason, we decided to do deep learning to improve the block list that we have for the dictionary-based method. Our main goal is to extend the block list automatically, and in order to identify new terms, we want to use the context that is found around the terms. Then, using that, we want to train state-of-the-art domain-specific deep learning models. And what we have developed is a multi-class text span classifier based on BERT models. But what is actually BERT? Again, if you're working in NLP in the past few years, you've probably heard a lot about BERT. BERT stands for Bidirectional Encoder Representation from Transformers, and it's a deep learning model that is very commonly used in NLP and also biomedical NLP in the past few years. What this model does, it has two main big parts. One is the semi-supervised training on large amounts of text. The original model was trained in the entire Google Books and Wikipedia corpus. And this model can process the English language. And then this serves as the basis for the second part of the model, the supervised training on a specific task. And here, as for any supervised training, we need a labeled dataset in order to do our work. What is great about BERT, and on top of everything else regarding its architecture, it's that it is truly bidirectional. It means that the model has full access to left and right context when dealing with a word. This is very useful during pre-training, where certain English words are masked, or words in general if we're talking about multilingual, and then after they are masked, the model tries to predict what is the word that is missing, the masked word. But we can take this into our advantage when we're actually fine-tuning or during the supervised training of the model in order to find words of interest that are masked, and the model learns the label for the masked word based on the context around it. And maybe this doesn't make sense, so let me give you an example. So in our task, we would like, for example, to detect organism or gene names in text. And the way we do it is that we mask out the words, and we want the model to start learning how things look around an organism or around a gene. So, in order to train a BERT model, we need positive and negative training examples. And of course, one could manually sit down and annotate such examples and find them, but on the other hand, there are smarter ways to get our hands on millions of examples. And what we thought of was to use 3 different named entity recognition systems, namely the Tagger, the EVEX system, and PubTator, and get their consensus. And the consensus of this method is text spans, where the methods agree on what and what not to tag. So that way we can get our positive and negative examples of contexts. And using a consensus means that probably the recall is going to be very, very low, because we will use all the names that only 1 or 2 methods detect. But this will give us a data set that has a very high precision, and that gives us a very good data set to train on. So the positive and negative examples of context come from 5 classes, and we have specific entity types that are tagged, and these are 4: the genes or gene products like proteins, chemicals, diseases, and organisms, and nothing tagged, which serves as the negative class. And then we have the model to train, and BERT is a very good model, but there are more domain-specific models, and we decided to go with the biomedical version of BERT, otherwise called BioBERT. But what parameters do we use to train this model? And based on literature searches and on initial experiments, we have identified a set of hyperparameters. We did a grid search, and we found the best ones to have a model that has a 97% F-score. And using that model, we produced a ranked list of the most problematic names, and we wanted to evaluate its quality. That was the next step. And the question is, can we use this list as is by the named entity recognition system, or is it only useful to guide the manual curation effort? Our hope is that the former is the case, so we can use this list as it is. But in any case, in order to find that out, we need to first check the terms manually. So the idea is that what we do now in order to find that out is that we get all the context for all the Jensen Lab Tagger matches in the literature. We run predictions on the fine-tuned BioBERT model that we have, the one that has the best score on the test set. We get a probability for each match, for each sentence that is passing through the model. We aggregate the probabilities of all the matches and assign 1 score per term across the literature, and then check if that score passes a threshold that we've set. If it does, we update the global block list with this term, and if it doesn't, we proceed to the next term. And another nice feature of using a deep learning based model is that we can aggregate the probabilities and assign 1 score per term per document. So thus, this allows us to create local block lists. Again, we are checking if the score goes above a threshold that we set and update the local block list or not. As you can imagine, if scaling is a problem for creating global lists, local list is just not possible to create. So this gives us the opportunity to do that. But how do we find these thresholds? Well, once again, we have to check the lists manually. And after some manual checking and using a lot of set of parameters to do these checks, we end up with a set of thresholds that we use for the global lists. And similar work is done for the local lists, and with the automatic block listing extensions, we have generated a global list of almost 300,000 terms, more than 300,000 terms, and a local list that have more than 500,000 names blocked in more than 500,000 documents. And when it comes to unblocking names that are globally blocked in specific documents, we have almost 30,000 protein names unblocked. But how do we actually know this works? I mean, we certainly see this list because we manually check them, but we need some sort of benchmarking to be able to claim that this works. So what we did is we did 4 different runs with the tagger, one without any block list and without any regular expression, to see like what would happen if we just run tagger without anything, one with an automated block list only generating by BioBird and without doing any manual cleanup as we did for the work that we actually used it for, one with a manually curated block list only, and one with the combined list of automated and curated block lists. So number 3 is what we were using before BioBird, and number 4 is what we are actually doing now. And we decided to benchmark this against KEGG. So one might wonder, KEGG is a database that has pathways, and from there we can get a functional protein-protein association gold standard. So how is that useful to benchmark named entity recognition? Well, we actually want to check if the pairs that we get after blocking specific names are still good, because this block list, as I said in the beginning, is useful for several databases that have associations, and that's what we care about. So that's why we decided to move forward with doing this benchmark. And the results for this benchmark is that obviously using no block list really doesn't work that well. But then when it comes to automated only, curated only, or curated plus auto, so what we are doing now, we really don't see that big of a difference between the 3 methods. Even when we zoom into the highest scoring pairs, yeah, the curated plus auto seems to perform better in this benchmark, but the differences are not that significant. And the main reason for that is that we are using a gold standard, and that is KEGG. So we decided that maybe a better idea would be, instead of going with the gold standard, so in that sense we have already probably manually added bad names for things that are forming a gold standard in the global curated list before moving forward into generating an automated one. It would be better if we could actually calculate the precision and recall before and after automatic additions to the block list. So the idea is that we go and manually check the original precision of the Jensen Lab tagger, and I will present here what we did for the genes and proteins. So we checked 1,000 random protein matches from the curated block list only, and there we can calculate the precision of the method. So the Jensen Lab tagger precision with the curated block list is 87.7%, so it's already very high. But then we said that we can manually check the new precision of the tagger when we actually have some matches blocked by the automated list. And how we did that is that we checked 100 random protein matches that were blocked by the automated list. And then we calculated the precision again, and it was 96.8%. So in that sense, we had a 9.1% increase in precision. The problem is, how can we really calculate the recall in the beginning and in the end? We have to go in, check documents in detail, but we don't need that in order to check the relative change from one to the other. So we already know that we have a 9%, more than 9% increase in precision, so our method would work well if we are not losing a lot. And this is actually the case. Our calculations show that we lose less than 1% in recall. So overall, the new block list can be directly incorporated into the Dagger, and then it can be immediately publicly available through all the RESTful APIs that are serving the databases of our lab. And as we've shown, this leads to a significant improvement in precision. It actually is close to many machine learning-based methods. Plus, it allows us to enhance a lot of biomedical dictionaries that way. I would like to thank everyone in my lab, thank everyone from the Turku NLP lab where I have been doing my external stay and have been closely collaborating in this project with the group leader from the group, Sampo Pyysalo. Thank Lars for his supervision on the project, and thank all of you for your attention.